Yeah.
Hi guys, you're welcome to my channel. Today we are going to be looking at number 3 question on Neco practical, and that is on electricity. When you talk about the concept of electricity, it's a constant aspect of physics practical that all exam must test, and it used to be in question number 3. Now for this year, with the instruction given, we see that we want to verify Ohm's law. Now, I would like to discuss some certain facts before going into the experiment, so that will serve as a guide when we are doing the experiment for you to know either you're on the right track or not. Okay, now, look at something here. We have that from Ohm's law, V equal IR, where I is the current and V is the voltage, and R is resistance. Now, if resistance is constant, whenever you increase the voltage, the current would also increase. If the resistance is constant, whenever you increase the current, the voltage will also increase. Why? They are directly proportional to each other. But if you observe this experiment now, in some cases, examiner might actually let another thing to be the constant instead of resistance. In some cases, you can have the current to be constant. They will like, if the current is constant, what will happen to the voltage if the resistance increase? Or what will happen to the resistance if the voltage increase? Or they can decide to keep the voltage constant and ask you what will happen to the resistance when the current increase, or what will happen to the current when the resistance increased. But for this year, from the given word, from the given question that we have here now, we see that the voltage is what is constant. The resistance keeps changing in value. And as the resistance changes in value, examiner wants to know what will be the value of the current. Is current going to increase or decrease? That's what you need to know now in order to guide your reading. Now watch. From here, if we assume or keep V constant according to this experiment, you will see that I is actually equal V divided by R. Note that V is a constant. So if V is a constant, it shows that I is inversely proportional to R. Therefore, as R increases, in the current I is said to do what? To decrease. As I increase, R is said to decrease. As R increase, I is said to do what? Decrease. That is the relationship between them. So this will guide us now to know if our reading is actually correct or not. And if we also want to manipulate the result, or in case we have a faulty apparatus or some reason, there's a way we can also use this to get what the actual reading should be, which we are going to consider at the end of the experiment. So let's go to the main experiment now. The question says you are provided with a resistor X. This is our resistor X. It used to be 2 ohms. And your teacher or the lab you are working with might not have 2 ohms resistor. They might probably have 3 ohms. They might probably have 1 ohm. All you need to know as a student or a teacher is that note the value of the resistor X. But for my own, it is what? 2 ohms. Cool. And what's the next thing? A resistance box R. Here is my resistance box. Here is my resistance box. Okay? Connecting wires. All my connecting wires are already on my terminals for the apparatus. I have my connecting wires on them already. Okay, what next? A key. This is a key. This is called a key, which you can also call a switch. Okay? And what again? And a battery. So this is a battery. It can also be called a cell. And ammeter. This is ammeter. This is what? Ammeter. Okay? So what's the next thing? We've seen the whole of the what? Apparatus given. What's the next thing to do? Roman figure 1. Connect the circuits as shown in the diagram above. This is where students have problem. How to connect what? The circuits. But it's quite simple. Just look up. Anywhere you see a line in a circuit diagram, that line implies wire. I mean connecting wires. So we are going to trace the wire, and we trace each one, each branch. When you say branch in a circuit, branch means a load in a circuit. Like this is a cell, it's a branch. This is a key, it's a branch. This is ammeter, it is a branch. This is resistor, it's a branch. This is the resistance box, it's also what? A branch. Now, let's go on to set up the apparatus as we have it like this now, okay? Okay, so we have the key. This is the key here. The key is connected in series with the cell. But I would like you to note something. The long pole here of this cell is the positive pole, and the short one is the negative pole. If you see this now, it shows that we have two cells. Are we getting this now? This shows what? Two cells, because this is positive, negative, and this is key. So when you look at the cell, the key and the ammeter, they are both in series. So we are going to do the same thing here now. This is my cell. Can you see? And my cell is said to be, so this is my cell, this is cell, and this is my key. I see it now. This is my what? My key going to the negative terminal of the what? Of the cell, and the other end of the key is going to the positive terminal of the, what is it called? The ammeter. Now, my own ammeter here is capable of reading 5 ampere, but I want an ammeter that can only measure what? 3 ampere. Although this can measure up to 5. So the first terminal here indicates that from 0 to 3. And if I connect the wire to the second terminal here, it means I want it to read 5 ampere. So that's why you see it connected to the what? To this. And when you look at it, we have 2 readings on it. The one below is reading what? For the 5 ampere. And the one above is for the 3 ampere. So when we are taking our reading, we consider the above reading, since we want it to read within what? 0 and 3 ampere. Cool. So we have it like this now. So this is the negative terminal of the key. The positive terminal of the key needs to go to the positive terminal of the ammeter. So we have it like this now. Okay, so the negative terminal of the ammeter is said to go to what? It's said to go to our resistance box. Okay, here is our resistance box, and this is the negative terminal of the resistance box itself. So we have it connected like this, and at the same time we have our 2 ohms resistor that is in parallel. The 2 ohms resistor is in parallel. If you look at it now, you can see they are parallel to each other, parallel to that of the resistance. So this is the negative terminal of it, the negative terminal of the 2 ohms resistor as well. Okay, then we have the positive terminal of the resistance box to be connected to the positive terminal of the cell, the one going through, sorry, of the key, the one going through the cell. So we are done with our connection now. So if you look at it, the cell, the key, the ammeter, then we have our resistance X parallel to the resistance box. So okay. So, and I think we can now we can go on with our experiments now to take the reading. So let's test run what we have. Now mind you, when the key is on this thing like this, it shows that it is on. When you open the key, it shows that it is off. But it's not like that on a resistance box. When I remove the key on a resistance box, that is when it is in use. And when I close it, that's when it's not in use. Are we together now? For the key, when the key is closed, that's when it is in use. If it is open, it is not in use. But for resistance box, when it is open, that's when it is in use, not when it is closed. Is that taken now? Cool. Now, before we run anything on the resistance box now, let's try what we have here. Okay, you can see the reading on the ammeter now. Can you see? Okay, I remove it now. Can you see again? Are you seeing it now? So if your reading, if your ammeter reading should go in the other way around, that shows that your connection is faulty. Are we making sense now? That shows that your connection is what? Faulty. But you can see it's going the appropriate way that it's supposed to go. Are we together now? Okay? So permit me to change this cell to the other one. I think this is very weak because the current that is reading is very, very small. And that's why it's advisable that you get what? You get a new battery if you are carrying out the experiment. Okay? Okay, cool. Now that we've sat in with what we have, now let's go to the question back now. Okay, so set the resistance box R 2 ohms and close the key K. So now that you are yet to set up your resistance to a certain value, let your key be open. Now we are asked to set the resistance box to 2 ohms. So for the resistance box, 2 ohms, I remove the 2 ohms here. What's the next thing after that? Read and record the value of current I on the ammeter. This is where the work lies now. Permit me to clean this now, since we are done with this aspect. And this is where you know how to get your tables. And now, when it is 2 ohms, you are asked to measure what the current will be. Roman figure 4, evaluate R inverse. That is, we need what? R inverse. Repeat the above procedure for 4 other values of R. So we're done. It means that in our table, we are only going to have a column for R. We are going to have column for I. We are going to have column for R inverse. So we can just draw our table like that. Okay? So we have this to be our serial number. The experiment is to be done 5 more times. Then this is our resistance in ohms. This is our current in ampere. And this is our resistance inverse in inverse ohm. Are you getting this now? Cool. So we are given resistance 2 ohms. That's 2.00 from the question. What will be the corresponding current? So let's determine that now. Okay. You don't need to stress yourself over that. Don't just worry. So I will close the key since I've set my what's it called to 2 ohms. So I have this. So according to my reading now, I have 2.80 here on my ammeter. So I will put that down. Ammeter read 2.80. Forget about arrow inverse now. It's something we are going to get with our calculator. So let's go on. When it is what? 4 ohms. That's 4.00, 6.00, 8.00, and 10.00. Okay? So I have to increase my resistance now to become what? 4 ohms. So I will remove another 2 ohms. Are you getting this now? So when I remove another 2 ohms, I have this. Okay. Okay, there's a mistake here. Sorry. So better still, if you have the what's it called, a sellotape, you can just use it to clip your negative pole to the battery and this. So the masking tape will do that. Okay, cool. So this is going to give us 2.06. 2.06. 2.06. So when it is now 6 ampere, how do we get that? I need to close the 2 ohms. So I'll remove 1 ohms and 5 ohms. So removing the 1 ohms and 5 ohms, I will take the reading again. So I have 1.80. 1.80. So when it is 8 ohms, okay, remember this is 6 ohms, I'll remove what? 2 ohms, making what? 8 ohms now. So okay, this is giving us 1.68. 1.68. And lastly, when it is 10 ohms. Okay, so we have a column for 10 ohms here. So I take it out, 10 ohms. So this is 1.60 now. Okay, let me confirm. This is 1.60 now. When it is 10 ohms, we have 1.60. Okay, so now that we're done with the reading of the ammeter, we can now get what? Our inverse of resistor. So 1 divided by 2, we have 0.5. So it's going to be 0.500. And 1 divided by 4, that's 0.250. 1 divided by 6, 1 divided by 6, that's 0.167. And 1 divided by 8, that's 0.125. And 1 divided by 10, that will give us is 0.100. Okay, I'll still have to recall this for the benefit of those that will be doing physics for the first time. The arrangement of your decimal place is quite important when you are dealing with this experiment. Any experiment in physics, Whatever, your serial number will not be in any decimal place. I want to get them just in one significant figure. Then the reading given to you in the question should be in 2 decimal places. Although there are some rule that states that you should put it in 1 decimal place, but preferably put it in 2 decimal places so that your table will be sequential. Are we together now? And whatever reading that you are getting from your ammeter should always be, or any of your measuring instruments should always be in 2 decimal places. Reading given to you in the question should be in 1 decimal place, or you put it in 2 decimal places. And the reading you are taking from your apparatus should be in 2 decimal places. And the reading that you are getting with your calculator, that is the evaluated value that you are getting, should be in 3 decimal places. Do we understand that now? Cool. So if that should be the case now, we are done with the table. And mind you, as a student, your table, you should not what? Cancel. Are we together now? Okay, now that we're done with the table and we've understand what decimal place the table should be, mind you, as a student, please don't shade. For every column or row that you shade, there is a mark that you are going to lose. Please. And your table of value takes the highest mark out of the mark awarded to every question, including your graph, will come in there. Okay? Now, we've gotten the readings now. What's next thing? Tabulate your readings. That's what we've done. We've tabulated the reading and plot a graph of arrow inverse on the vertical axis and I on the horizontal axis, starting both axes from the origin 0, 0. Watch something here. By the time you plot the graph of arrow inverse on vertical axis and you plot the graph of I on the horizontal axis, do you know what you're likely to have? Let me show you. You know, your slope is going to be changing arrow inverse divided by what? Changing I. Watch. Our x, which is the slope, is there going to be what? 1 over r divided by I. Are you seeing this now? 1 over I divided by what? Divided by 1 over r divided by I. That's what we tend to have, isn't it? Okay? If that should be the case now, we therefore have that. Okay, for better understanding, let me take it like this now. This is 1 over r, 1 over 1 divided by r over I. Are you seeing it now? S equal 1 divided by what? R over I. So if I cross multiply here, you know, if I have this now, the other way around, S will become what? I divided by what? R. Are you seeing this now? So this is what our slope will be. That is the inverse of what? Of our voltage. Because our voltage is actually what? Is actually IR. Are you getting this now? Okay? Let me see something here. Watch now. What I showed you here earlier, that I want to bring out something on that slope, but I think I'll come back to it when I get to the graph. Not actually seeing clearly like that. Okay? Watch now. You see that when you increase what? The resistance R, what happens to R? You see that it's decreasing. That is how you check if your reading is actually intact or not, as a teacher or as a student. Now, how do you manipulate this reading? Let's see. How I want to get the reading. I have a battery of 1.5 volt, 1.5 volts each, which is 3 volts. Our V is equal to 3 volts. We want to know the value of I, and we are given R to be 2 ohms at the first instance. If you look at the cycle diagram, you see that the resistance X and the resistance box, they are parallel to each other. Abi? So when they are parallel to each other, the equivalent resistor is what will determine the current that is flowing in the circuit. And when you have two resistors that are parallel to each other, the equivalent resistance is going to be what? The product over the sum. Therefore, when the resistance is 2 ohms, the total resistor in that particular circuit, when the resistance is what? 2 ohms. The total resistance in that circuit is going to be 1 ohms. That will be 2 times 2. Remember, my x is what? 2. 2 times 2 divided by 2 plus 2. That's 1 ohms. When the resistance is now increased to 4 ohms, that will be 4 times 2. That's 8 divided by what? 6. 8 divided by 6 will give us 1.333, if I'm not mistaken. So this will be 1.33 ohms. Are you seeing it now? When R is what? 6. That will be 6 times 2, that's 12, divided by 8. 12 divided by 8 will give us what? 12 divided by 8. That will give us 1.5. So this is 1.50 ohms. When R is 8 ohms, that will be 16 divided by what? 10. 16 divided by 10, that will be 1.6. 1.60 ohms. When R is now 10 ohms, that will be 20 divided by 12. 20 divided by 12, you have 1.67. So 1.67. This is the equivalent resistor that wants to determine your current. Are we together now? Okay? If that should be the case, now let us get the corresponding currents now. I want to get the O table for the manipulation. Watch you. This is S, the serial number 1, 2, 3, 4, 5. And here is what? The resistance in ohms. This is 2, 2.00, 4.00, 6.00, 8.00, and 10.00. Are we together, guys? Cool. Now, what will be the corresponding current? Ampere. Remember that when the resistance box is set to 2 ohms, the equivalent resistance is 1 ohms. Abi? And from Ohm's law, current is equal to V divided by what? R. And our voltage is what? 3 volts. So 3 divided by R, which is what? 1. 3 divided by 1, that will give us what? 3 ampere. So 3.00. Are you seeing it now? Okay? Good. Then the next one is what? 3 divided by what? 3 divided by 1.33. What are we going to have? 3 divided by 1.33. Our result is 2.26. 2.26. Then the next one, 3 divided by what? 1.5. 3 divided by 1.5. Our result is what? 2.00. And the next one is 3 divided by what? 1.60. 3 divided by 1.60. We have what? 1.88. Then the last one is 3 divided by 1.67. Our result is 1.7. Okay, 1.80. Are you seeing this now? So our R inverse is still the same thing as what we are going to have there. Is 0.500, is 0.250, 0.167, is 0.125, and 0.100. Have we seen the table now? You look at this now. Now let's go back to what we have when we are doing our experiments. If they are very similar, this is 3.00, this is 2.80. This is our 2.26, this is 2.06. This is as a result of what? Experimental error, which examiner is actually expecting to happen. So if you are manipulating, you should try as much as you can to reduce it by probably 0.5 or 0.1 or 0.4 or 0.3, so that you'll be able to cater for the error that might probably occur occur in your experiments. Are you getting it now? Because if you decide to use it like this, examiner will know that you actually manipulate, because this is giving the expected value. Is that taken now? So if that should be the case now, we're done with that. So let's go to the plotting of the graph and see what our result will look like. Okay, so we're about to plot the graph now. According to the question, we'll plot the graph of arrow inverse against I. Now, the first thing to write is the title of your graph. That is graph of arrow inverse against I. So the next thing is the scale of your graph, so which is what we want to determine. Our arrow inverse is to be on our vertical axis, right? So you count 1, 2, 3 first. You place your ruler there. Okay. So we check. The maximum value here is 0.5 and the minimum is 0.1, right? So let's check now. If I use a 0.1 interval as my unit, 0.1, 0.2, 0.3, 0.4, 0.5. and 0.6. I think 0.1 is okay. Have you? Okay. Don't mind this nonsense higher condemn guy. So let's proceed, please. So we can rule our line here. Okay. So if we have this now, we quickly come down here. We say 2 centimeter represents 0.1 units on vertical axis, or you say on arrow inverse axis. Don't say y axis, please. Okay, so the next thing now is to get the unit of the horizontal, that is the scale for the horizontal. We count 1, 2 and drop our ruler there. So the maximum value there is 2.8 and minimum is what? 1.6. So we try by using what? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. It's not going to be enough. Let's increase to 0.2, 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4, 1.6. It's not going to be enough. So let's increase it to what? 0.5. 0.5, 1, 1.5, 2, 2.5, and 3. So I think 0.5 is awesome. So we rule our straight line here like this and we turn it. Cool. So we have that 2 centimeter represents 0.5 units on horizontal axis. Okay, so if that should be the case, we are starting both axes from origin 0, 0. Awesome. Okay, so let's label now. This one is going to be 0.5. This will be 1.0. This will be 1.5. This will be 2.0. This will be 2.5. And this will be 3.0. And this is 3.5. Cool. So this is going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8, and we have 1.0. Okay, so do we get this now? So now let's go on now by plotting the graph now. Okay, so when the current is 2.8, the resistance inverse is 0.5. So 2.5, this 2.5, 1, 2, 2.6, 1, 2, 2.7, 1, 2, 2.8. For you to know the value of all these small lines, I've explained that in my previous video on how to plot the graph, so you can check that to know how we come about it. So we'll go down to our R inverse, which is 0.5. So this is 0.5 here now. Okay. So please don't forget to indicate what you are plotting here. Arrow inverse in ohm inverse and current in ampere. Okay. So the next one now is 0.25 to 2.06. So this is 2 here. 2.06. Okay. So approximately 2.1. So 1, 2, so 2.1. So I place it on 2.1. Down to where? 0.25. 0.25. So this is 0.2, 1, 2, 3, 4, 5. So this is 0.25. Okay, what's the next thing there now? The next thing there now is 1.8 to 0.2. Let me see that. 1.8. So this is going to be 1 to 1.6, 1.7, 1.8. So this is 1.8 down to where? 0.17. Okay, so this is 0.1, 1, 2, 3, 4, 5, 6, 7. So we have this. So the next one is 1.68 to 0.125. 1.68, so let us 1.7. So this is 1.7, this is 1.6, and this 1.7. So we have 1.7 here, down to 0.125. 0.125, that's approximately 0.3. So we have 1, 2, 3. So this is 0.3 here, okay? Okay, which other one there? So last one, 1.6 now to 1.1. So 1.6 is here, so we have it here. So this is 1.6 and this is 0.1. Okay, so we can then rule our straight line. So we have this now. Okay, so this is picking this now. So I have this now. So this is our graph now. So pick these three. So the slope, which you already know how to go about. So let me pick it here so that it will be a bit wide. Okay. So you have this now. Here also. You have this, right? This one down like this. And it's cross here also. So we have this now. So this is going to be our change in the arrow inverse. So our change in arrow inverse. Let's change in arrow inverse, and this is going to be a change in current I. So change in current I. So the slope S is going to be change in arrow inverse divided by what? The change in I. So is that taken off? So whatever result you have here is going to be the value for your slope. Is that taken off? So I want to get something here. I was thinking that the slope is supposed to give us the what was it called before? The so-called voltage. Voltage is IR. So let's see. This will be giving me what? 1 over R divided by R. So this is just going to be 1 over RT. Are you seeing this now? So if you look at it now, our result is going to be the voltage inverse. That's what I want to show on the board the other time. Okay, but because of my mindset, I'm thinking that we should be having voltage, but we have voltage inverse. So our slope should be corresponding to 1 over 3. Are you getting it now? So if you check your slope value, correspond to what? Well, you know, 1 over 3 is 0.3333. So our slope should be something similar to this. So at this junction, we're done with electricity. So thank you. You can now watch the 3 videos now on our channel. And if you are yet to subscribe to the channel, don't forget to do that. Thank you.